Now next we'll come to thermochemistry. What is thermochemistry? The branch of chemistry which deals with the energy changes accompanying a chemical reaction is called as thermochemistry. What does it do? The branch of chemistry which deals with the energy changes, that is the heat changes accompanying a chemical reaction. Means when a chemical reaction is going to take place and due to which some heat will be either evolved or absorbed, or some energy will be either evolved or absorbed, that is called as thermochemistry. And the equation which deals with it is known as the thermochemical equation. We can say that the equation which is dealing with this particular reaction, by which we are going to find out the different aspects of thermochemistry, is known as the thermochemical equation. That is when a balanced chemical equation not only indicates the quantities of the different reactants and products, but also indicates the amount of heat evolved or absorbed. Got it? It's known as a thermochemical equation, we can say that. Got it? So in this way, based upon these thermochemical equations, we have got, for exothermic reactions, we know that del H value is taken to be as negative, and for endothermic reaction, del H value is taken to be as positive. See, you have to remember certain things for thermochemical reaction. That is, del H is positive for endothermic reaction and del H is negative for exothermic reaction. That is, in exothermic reaction heat is evolved and in endothermic reaction heat is absorbed, so to say. Now, unless and otherwise mentioned, del H values are for the standard state of the substance. If you are not mentioning it, suppose it is not mentioned whether the value is standard value or calculated value or experimental value, we consider it to be a standard value only. We consider it to be a standard value, means the value which is given to you in your numericals, in your question, it is considered to be a standard value unless and otherwise it is mentioned. We can say that the coefficient of different substances represents the number of moles reacted and the number of moles formed. The coefficients like 2H2O, so two molecules of water is being formed. That's quite simple, isn't it? The coefficient it represents. The physical state has to be written, solid, liquid, gas, it has to be mentioned. Or aqueous, AQ, it has to be mentioned. Got it? The physical state, it is very, very important. Of different substance has to be mentioned. Got it? And the heat evolved or absorbed, that also has to be mentioned. How do we mention it? Heat evolved or absorbed? I told you already. If del H is negative, that means it is evolved. If del H is positive, that means it is absorbed, so to say. Okay. Now next is, if the coefficient of the substances are multiplied or divided. Alright, this is a very important point. If the coefficient of a substance is multiplied or divided by some number, the value of delta H is multiplied or divided by the same number. Suppose the equation I am writing it out. Got it? I have got a certain value of delta H. Let us say X. I am dividing the equation by 2. So delta H should also be divided by 2. That is X by 2. The value will be. So when you are multiplying or dividing a particular equation by a number, the value of delta H should also be divided or multiplied by the same number. Listen carefully. Understood? Remember it. Very important, this one. If the reaction is reversed, the sign of delta H changes, but the magnitude remains the same. If a reaction is reversed, alright, the sign of the delta H, suppose in the forward direction, if it is negative, if I am reversing it, means I am writing in the backward direction the reaction, then the sign becomes positive, but the magnitude will be the same only. Magnitude means the value will be the same. Let us say if it is in the forward direction minus x kilojoules, the value is minus x kilojoules. In the backward direction, the value is x kilojoules. Negative becomes positive. We can say that. So the sign changes, but the magnitude remains the same, so to say. Alright, so these are the points you need to remember while solving the questions upon thermochemistry, upon thermochemical equation, so to say. Now, next is, what is heat of reaction? The first is your heat of reaction, denoted with a letter that is delta HR. We can say that. Change in heat of reaction is said to be as. Heat of reaction means HR, and change in heat of reaction is delta HR. Change in heat of reaction means product minus reactant always. That is heat of the product minus heat of the reactant. Alright, so one thing children, listen here, that is in thermochemical equations, always whenever you calculate the change for any particular thing, change in heat of combustion, change in heat of neutralization, change in heat of reaction, change in heat of sublimation, change in heat of atomization, alright, change in heat of transition. Alright, so any change of heat you calculate in thermochemistry, so to say, your formula is always heat of the product minus heat of the reactant. Your formula is always heat of the product minus heat of the reactant. Remember it. Don't get confused. Your formula is same. always heat of the product minus reactant. In previously also we have done it the same thing, like internal change, internal energy change, enthalpy change, always what we have done, product minus reactant. So here also same thing, product minus reactant. So no need to get confused, nothing new it is. Got it? Fine. So the amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactant as represented by the chemical equation have completely reacted is called the heat of reaction or enthalpy of reaction or energy change of a reaction. If in a particular reaction, when you are writing a reaction and the reactant is completely used up, the total number of moles which is being used up completely, we can say that. Alright, it has completely reacted, and due to which certain amount of heat is evolved or absorbed, that is called the heat of reaction. We can say that. That is known as the heat of reaction. So hence I said the amount of heat evolved or the amount of heat it is absorbed in a chemical reaction when the number of moles of the reactants as represented by a chemical equation have completely reacted to form a product is called as a heat of reaction, or the what you can say enthalpy of reaction or energy change of a particular reaction, so to say. Alright, so if the quantities of the reactants are doubled, here you need to remember, if the quantities of the reactants are doubled, I have said you already, the heat of the reaction is also doubled. I said na, ki when the reaction is divided or multiplied by a particular number, then the heat change also changes accordingly. So if the reaction is multiplied by 2, if the quantities are being doubled, then the heat change is also being doubled. It will become 2x. Suppose if x is the initial heat, and if you are multiplying the reaction throughout by 2, then their heat change will now be 2x. Whether it is evolved or absorbed, that has to be seen. Alright, fine. Now, allotropic modifications. There are certain factors upon which the heat of reaction depends, we can say that. One is your allotropic modifications. When the allotrope changes, for example, suppose when you are using graphite and when you are using diamond, and both you are burning in air, then the amount of heat evolved in both the cases is different. That is what I want to say. That is allotropic modifications. Got it? I am burning graphite in oxygen. It produces carbon dioxide. I am burning diamond in oxygen. It also produces carbon dioxide. No doubt. There is no change in the reaction. C plus O2 gives CO2. The reaction is. But the heat change in both the case is different. The heat evolved in both the cases is different. In graphite, the heat evolved is different than that in diamond. So remember that allotropic form, when it changes, the heat change also changes. Alright, listen carefully, these things, it will be used in numericals. Listen carefully. Alright, so if in a particular reaction C plus O2 and C is diamond, if in a particular reaction C plus O2, C is graphite, then the heat change is not the same. Even if both are C. Chemically both are written C plus O2 gives CO2, C plus O2 gives CO2. But the heat change in both the cases are not the same, it is different. Got it? And the allotropes are different. Next is concentration of the solution. Heat change occurs when a solute is dissolved in a solvent. When a solute is dissolved in a solvent to form a solution, then the solution gets diluted. So the heat which is being evolved or absorbed is known as the heat of solution, which is said to be as. So it depends upon the concentration of the solution also. The heat of reaction depends upon the concentration of the solution, as I said. Next, it depends upon the temperature also. The heat of reaction depends upon the temperature at which the reactants and the products are taken. At what temperature the reactants and products are carried out. That means, if suppose a reaction is being carried out at 298 Kelvin, that is room temperature, so to say, and if a reaction is carried out above 298 Kelvin, that is above room temperature, that is, let us say, at 310 Kelvin, do you think the heat of reaction in both the cases is the same? No. The heat change in 298 Kelvin in a particular reaction is different from that at 310 Kelvin, which is again different from 340 Kelvin. So as the temperature changes, the heat change also changes, that the heat of reaction also changes. Alright, as the temperature changes, the heat of reaction also changes. But we can say that. The conditions of constant pressure or constant volume, definitely whether the reaction takes place at constant pressure, constant volume, that has to be seen. If it is constant pressure, like heat evolved at constant pressure, just now we discussed, which is Cp, and heat evolved at constant volume, which is nothing but your Cv. Is Cp and Cv both the same? No. Cp is equal to del H by delta T. Their enthalpy is being taken. And Cv is del U by delta T, where internal energy is taken. Got it? So it depends there. Now next is standard enthalpy of a reaction. As I said you already, the enthalpy change of a reaction depends upon the conditions under which the reaction is carried out. We can say that. Hence, it is very important to specify the conditions. If the condition is not specified, it is taken to be as the standard conditions. It is taken to be as the standard condition, so to say. So standard heat enthalpy of a reaction is enthalpy change accompanying the reaction when the reactants and products are taken in their standard state. Alright, standard enthalpy of reaction is known as the enthalpy change accompanying the reaction when the reactants and products are taken in the standard state. Now, based upon this, we are having the different types of heat of reaction, heat of reaction we are having it. Alright, the different types of heat of reaction or different enthalpies of heat of reaction we are having it. The first is your enthalpy of combustion, heat of combustion. Heat of combustion we denote it by letter that is delta CH. Here also we can write delta HR, or in certain books you will find it out, in certain symbols it is written in this way also, delta RH. The same it is. It is nothing but HP minus HR. That does not make any difference. This is also heat of reaction, this is also heat of reaction, anything it is. So heat of combustion is delta CH, we can say that. Heat of combustion. Combustion means what? Burning, we can say that. So heat of combustion is defined as a heat change. Usually the heat evolved. Generally whenever substance burns, heat of combustion means heat is nothing but negative. The value is negative, always remember that. Whenever a substance is burnt, heat is being evolved. It is being not absorbed, evolved it is. Alright, so when 1 mole of the substance is completely burnt or oxidized in oxygen. When 1 mole of a substance is completely burnt or oxidized in oxygen, that is called as heat of combustion of a substance. And heat of combustion is always negative, we can say that, because always it is evolved, so to say. Alright, like C plus half O2 gives CO2. So heat change is what here? Negative. The value is negative. Whenever substance is burnt, we can say that. Clear? Now for standard value, what we do is that for standard value, for example, for standard heat of combustion, what it will be? Only the difference is that the symbol is delta CH naught. Now when it is taken to be a standard condition, when the reaction is carried out at 1 atm pressure and under 273 Kelvin, that is said to be a standard, what you can say, heat. Any sort of reaction. Got it? Any sort of convention, when it is carried out at 1 atm pressure and at 273 Kelvin, it is said to be as a standard condition. It is known as a standard condition. For standard condition, what will be the symbol? This is the symbol for standard condition. Not, we'll put it. For symbol, it is this one. Like standard heat of reaction, what it will be? Not. 1. We'll be putting a not here. That is standard heat of reaction, so to say. For standard conditions. Like for standard heat enthalpy of combustion, what is the definition? What is the definition? It is the amount of heat evolved when 1 mole of the substance under standard conditions. Again I repeat, standard conditions means under 273 Kelvin and 1 atm pressure, we can say that. Or if you are taking SATP conditions, it will be 298 Kelvin and 1 bar pressure. Under SATP condition, that also is standard conditions, which is 298 and then 1 bar pressure, we can say that. Is completely burnt to form the products, also under standard conditions, we can say that. Clear? So whenever a reaction is carried out under standard condition, that is under STP or SATP, whatever it is. If it is STP, then 273 Kelvin and 1 atm. If it is SATP, then 1 bar and 298 Kelvin. Both are standard conditions. So whenever a reaction is carried out under standard conditions, the heat evolved or absorbed is called as a standard heat of combustion. But in case of combustion, always remember that it is always evolved. It is never absorbed. It is always evolved. It is never absorbed, so to say. Clear? So here it is delta CH naught is standard. Fine. Now next is the calorific value. The calorific value of a fuel or the food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of the fuel or the food. When 1 gram of the fuel or the food is being burned, or it is oxidized, so the amount of calorie, that is heat which is produced, which is measured in joules or in calories, is known as the calorific value, we can say that. For example, suppose you are taking methane, that's a fuel, got it? So when it is being burnt, on burning, when there is 1 gram of what you can say methane, how much energy is being produced? That is known as the calorific value of the fuel. Or suppose when you are eating the food, the amount of heat which is being produced by eating 1 gram of food, what you can say 1 gram of any particular food, the amount of heat which is being produced, which is being liberated, that is known as the calorific value. It can be measured in calories, Generally it is measured in calories because calorific value I am saying, or it is measured in joules also, we can say that. Clear? Now next is, after that, enthalpy of formation. Enthalpy of formation is denoted by letter delta FH, we can say that. Now if it is standard enthalpy of formation, it will be delta FH naught. F stands for formation, we can say that. Clear? So the enthalpy of formation of a substance is defined as the heat change, that is heat evolved or absorbed, when 1 mole of a substance is being formed from its elements under given conditions of temperature and pressure. Alright, when 1 mole of the element is being formed, 1 mole of the substance is formed from the element, we can say that. Clear? 1 mole of substance is being formed. For example, 1 mole of carbon dioxide is being formed from carbon and oxygen. So the amount of heat which is evolved or absorbed is called as the standard heat of formation, we can say that. Under standard conditions, the amount of heat which is evolved or absorbed, that is called as standard heat of formation, or simply it is called as heat of formation. Alright, again I repeat, that is nothing but the enthalpy of formation of substance is defined as the heat change, that is the heat evolved or absorbed, when 1 mole of a substance is being formed from its elements under given conditions. If the condition is standard, that is known as standard heat of formation. Otherwise, it is known as simply heat of formation, which is known to the letter delta FH. Now, one thing you must note it here, the standard heat of formation of an element is 0. Standard heat of formation of an element is always 0. For element, standard heat is always 0 because element we cannot form it. Element already exists. Alright, we are not making an element. We are making a compound. From element we are making a compound. The definition is we are making a compound. We are making a substance from its elements. So the standard heat of formation of element is always 0. Like when I write C plus O2, so standard heat of formation of C is 0, O2 is 0. But carbon dioxide will have certain value because carbon dioxide is being formed, so to say. So remember it, standard heat of formation of any element is 0, we can say that. Only those compounds are more stable than their elements whose delta FH naught values are negative. Alright, whenever we can say that this compound is being formed and if the value is negative, then definitely we say that the compound is stable in nature, because always remember that a compound is considered to be stable when the heat is evolved. When the heat is evolved, it is negative. Alright, fine. So greater the magnitude of the negative delta FH naught value, greater is the energy released, more is the energy released, and more stable the compound is. Alright, again I repeat, greater the magnitude of the negative value, that is delta FH naught, we can say that. Greater is the energy release, more is the energy release, and greater is the stability of the compound, we can say that. Clear? Now next is, similarly we have got the heat of neutralization, enthalpy of neutralization. That is enthalpy of neutralization of an acid or by a base is defined as a heat change. Usually the heat evolved, we can say that, when 1 gram equivalent of the acid is neutralized by a base. When 1 gram equivalent of an acid is neutralized by a base, so the amount of heat which is being evolved, there is a heat change, it's known as the heat of neutralization of an acid, and ultimately what it forms a neutral solution after neutralization, because what I am saying, heat of neutralization. So when 1 gram equivalent of an acid reacts with a base, got it, the reaction when it is being carried out in dilute aqueous solution, then the heat which is being evolved, that is called heat of neutralization. Generally, when any strong acid reacts with any strong base, like HCl, HNO3, H2SO4 reacts with NaOH, KOH, LiOH, etc. So the heat which is evolved is 57.1 kilojoules, we can say that. Got it? 57.1 kilojoules, because any acid reacts with any base. What is the general reaction? H plus plus OH minus, isn't it? Whether it is HCl or H2SO4 or HNO3, whether it is any base. So the general reaction is H plus plus OH minus. So the heat which is evolved is how much? It is 57.1 kilojoules. So if it is a weak acid or a weak base, then generally the value will be less than 57.1 kilojoules. Because for the weak acid we can't say the exact value, because we do not know what is the strength of the acid and base, how much acid and base is going to dissociate. But generally in case of strong acid and strong base, we know that it dissociates almost to 100%. Degree of dissociation is almost 100%. So hence we can calculate and say that in case of strong acid and strong base, the heat of neutralization is 57.1 kilojoules. Got it? And if it is weak acid and weak base, the value will be less than 57.1 kilojoules. For weak acid and weak bases, the value will be. Got it? In either case, whether it's a weak base or a weak acid, for example, weak acid is your acetic acid. weak base like ammonium hydroxide, the value will be less than that. We can say that. Clear? So in this way we come to the heat of nucleation. We know about the heat of nucleation. Thank you.